today's learning goal, even though we're still going to use all the other skills that we've learned in lesson 1.5, our learning goal, come over here with me. Come over here with me. Come over here with me. Thank you. I can simplify and solve equations. So we're still going to have to do, like I said, some of the same skills that we learned before today. But today, here's what's going to happen with some of our problems. They're going to turn out to be a no solution or an all real numbers solution. Meaning, we're not going to get like just x equals maybe 6 or x equals -2. Or we're not going to get just that one value solution. We're going to be led to a conclusion that this one means there is no solution for this one whatsoever. There is not a number on the number line that would make this equation true. Or it might turn out that all numbers on the number line would make the equation true. So then we can't name them all, so we have to state all real numbers. So the first type that we're going to explore here are that some equations have infinitely many solutions. In other words, we can't list all of them. There are infinitely many of them. Any number you pick off of the number line would be a solution. Well, when that's the case, there's a special name for that type of an equation. It's called an identity. So I want you to fill in that blank also. An identity, not an identify, it's an identity. So when we have an equation that has infinitely many solutions, the whole number line, we call it an identity. And I think you'll see why we can call it that in a little bit here. Okay, let's take our first practice problem here where we have the 6 minus 2x minus 1. And that is equal to the 4x plus 8 minus 6x minus 3. Boy, that looks like something we've been doing lately, doesn't it? What would be the first thing we would do in this problem? Add the opposite. Thank you, Preston. It would be, we have to change all those subtractions that we see in there to add the opposite. So it's going to become 6 plus what? Negative 2x. That's another subtraction plus what? Negative 1. So renaming the left side so that we have 2 additions instead of 2 subtractions. That's what we get. And then now we have some subtractions on this side. 4x. Well, that's already addition, isn't it? So do we mess with it? No, we just leave it as it is. But now we have a subtraction, so we'll change that to addition. And what are we going to add?
-6.
A negative 6x.
Plus -3.
Plus -3. Now, some of you are getting a little bit lazy, or maybe always have been, and want to change your ways. You need to always, when there are variables in the terms, you need to make sure they're there. When they're constants, then you're showing constants. You need to show everything. Some of you are just like, well, and it's a 3x, but I can just subtract 3. But not really. If they're x's, we got to keep working with x's, okay? So, next thing we're going to ask ourselves now is, can we simplify before we start solving?
Yeah.
Okay, what can we do? Anything on the left side?
But the 6 is not negative.
Okay, so we have these 2 constants, so they can be combined. What is 6 plus -1? 5. And then, does that negative 2x have anything to be put together with?
No.
No, so we just bring it along. How about the right side?
4x and -6x.
Okay, the 4x and the negative 6x can be put together. Okay, what do they become?
-2.
Negative 2, okay, and those are x's, right? Any other like terms that we can combine?
8 and -3.
Okay, so we've got our constants. This time I'm going to use a triangle around them so that I just have a different symbol because we're on the same side here. So 8 plus -3, what's that?
5.
That's a 5, so plus 5. Okay. Now, I want us to stop right here, and I just want you to see that. Do you see anything going on here?
Yeah, they're both just opposite, switched around.
Okay, so they both have a 5 on, a plus 5, right?
Yeah.
And they both have a negative 2x, don't they? Okay. So addition allows us to have these two trade places. Let's just have them trade places so we can see, you know what? There's something about these guys that's different than has happened to us before when we've been solving equations. Both sides are the same. I need to get my completed copy here to make sure that's where I wanted that, but okay. Yeah, both sides are the same. So right here, this is what, you know, we look at it and we say negative 2x plus 5, negative 2x plus 5. So we stop right there when we get it so that they look exactly the same, and we say, we call this an identity. One side matches the other. They're identical. So we call that an identity. And any number could actually make that equation true. Let's just try some. Let's just see if it works. Give me a number for x. Pick a number from the number line. 6, okay? So if we put 6 in there, we would take it times negative 2. What would that be?
12, negative 12.
Negative 12. What's negative 12? No, the x got replaced with 6. So 6 got put in for x, multiply it by negative 2, we get negative 12. What's negative 12 plus 5? Negative 7. Would that same thing happen over here? Yeah, we'd end up with negative 7 equals negative 7. True, right? So it makes it true. Hey, somebody pick a negative number for us. But remember, we're going to have to work with it, so be nice.
4.
Go ahead, Joseph.
Negative 5.
Negative 5, okay. So negative 2 times negative 5. What's that? Positive 10. And positive 10 plus 5 is 15. So would the same thing happen over here? Negative 2 times negative 5?
Yeah.
10 plus 5. So we get the same thing on the other side, wouldn't we? So it makes it true also. So do you think there's any number that we could possibly pick that would not make it true? How about 0? You know, 0 seems to, like, for some reason, it kind of like when it happens, we're like, oh, I can't have 0. Do you think we could have 0? What's negative 2 times 0? 0. What's 0 plus 5?
5.
Would that happen over here? Yeah. So can 0 be a solution also? Do you think we can name every solution that possibly would make this true? Do you think you can come up with one that would not? Anybody think they could come up with one that would not make it true? Why not?
Because they're both the same.
Because they're both the same. Whatever happens on one side is going to happen on the other side. They're going to keep matching each other, aren't they? No matter what we put in there, they're going to keep matching each other. So we are going to say, since any number can make the equation true, the solution to this is all, oh, I don't think that's what I want to be, infinitely many solutions. We're going to say all real numbers. All real numbers. That's our actual solution. So let's circle that, and then behind that, we're going to put, this is our solution. Okay? We actually have to state our solution, and that's how we have to state it. We can't begin to name every number on the number line. So what we say instead is all real numbers, because that's what the number line is made up of. So if this happens while you're solving, you stop right here and you say, you identify this as an identity. An identity tells you, you know what? That means any number I choose would make it true. So my solution is all real numbers. Okay, anybody have any questions about that? It's the only one we're going to practice of that type. So let's go down here to the next one then, where I say some equations have no solution. So we're really doing a new thing here, okay? Some equations have no solutions. So let's practice that one. What happens when there are no solutions, okay? So what's our first move in this problem?
Make all the subtractions and adding.
Yep, we got to change our subtractions to add the opposite. So 8x, we got an addition, we don't need to change that one. We have a subtraction, we need to change it to add what? Okay, what is it? Negative 9x, okay? And then on the other side, what do we have? 2 plus negative 1x. Because when there's not a number in front of the variable, we know we can put a 1 there. And then plus what? Negative 15. Okay. Okay. Do we have any simplifying to do?
Yeah.
Okay, what can we do something on the left side?
8x and the 9x.
Okay.
9x.
The 8x can be put together with the negative 9x. Okay. I'm still seeing this on some papers. And this is not correct. So don't follow my move here and do the same thing in your paper right now. Some of you are doing like this. You're saying, oh, I gotta subtract 9x. We're subtracting 9x twice on the same side. So guess what we're really subtracting? Not just 9x, but we're subtracting 18x altogether. Is that what we want to do? No. So we got to quit doing this. We can't. This is not how we show it. This is not what we want to do. We want to say, these guys are on the same side. I just need to bring them together. So what's an 8x plus a negative 9x? A negative 1x. So we end up with a negative 1x when we bring those together. Does that 6 have anything on this side it can be combined with? No. Okay. So it comes along. How about the other side? Is there anything we can put together? The 2 and the negative 15. And again, I don't want to see subtracting 2 twice on the same side or adding 15 twice on the same side because you're really then subtracting 4 or you're adding 30. And what we really want to do is just bring these guys together. So what is 2 plus negative 15?
Negative 13.
Negative 13 plus, does that negative 1x have anything to be combined with on this side? No. So we just bring it along. Okay, now, kind of looking a little bit like the last one, isn't it? How is it the same as the last one?
Negative 1x.
They both have a negative 1x, so they match, don't they? The negative 1x is matched, but do the constants match? No, and when the constants don't match, then we can't stop now and say this is an identity. The sides have to look exactly the same, and they don't look exactly the same. So what we're going to do now is we're going to have to go to work solving this one. We're going to see what actually happens, okay? So we can't stop and write the word identity. We have to solve. So what could we do?
Add 13.
Yeah, you know me. Come on, make me happy. You know I like to work with the variable term, not the constants.
Okay, so
Add 1.
Negative 1x.
Add 1, negative 1x? Okay, so would adding a negative 1x make it go away over here or over there?
No, you would make that into a positive.
And we
You're
gotta-
adding,
We got to add the opposite of that.
Yes, add the 1x.
So add 1x. Okay, I thought I heard negative 1x.
Well,
you
it's
did
a
say
negative.
No, that's a negative, so we need to add a positive, right? Is that what you were saying, Blake? Okay, I'm sorry. I'm just misunderstanding you. No reason to get mad at me. Don't hurt my feelings. Okay, what's left now? What's our equation say now? Did these guys cancel out?
Yeah.
Yeah, they're gone, aren't they? How about these guys? Did they cancel out?
Oh, yeah.
Yeah.
it'd be-
Oh, crazy. So what do we have? Got a 6 that's got to come down. It didn't get to cancel with anything. And then got a negative 13 that's got to come down. It didn't get to cancel with anything. What happened to the variable? Gone, right?
Could you still put like equals x?
So we what?
Could you still put equals x?
No. If there are no x's, we don't like say, well, but wait a minute, there's got to be. This is one of the situations that we're talking about today. They're going to look different. Just like the last one, it did have x's, but the sides matched. You know what would have happened if we would have kept solving this one up here, up above? Let me show you what would have actually happened if we would have kept solving that one. We would have had What would we do? Come on, remember now my rule, keep me happy. What would I do first? Plus 2 x, thank you. Okay, so we would add 2x to both sides. Well, would these cancel? Yeah. And look what would come down, a 5. Would these cancel?
Yeah.
Yes. And what would come down? A 5. So did the variable actually go away on this one too? It did. So here's the deal, the variable went away, but is this a true statement? Does 5 equal 5?
Yeah.
Yeah. So no matter what we would have put in for x, we still, and put it in even if we would have kept going with this, we still end up with something that's true. So this is what would have happened if we would have kept going over here. Here's what happens in this case, because we didn't have an identity. So because the x's, so there are no x's left, no x's left, they're gone, they disappeared on us. And the resulting statement is true or false? False. That's not true. 6 does not equal negative 13. I'd rather have $6 in my pocket than owe somebody $13 and not have anything. The resulting statement is false. There aren't any numbers that could make this equation true, no matter what we tried. We could sit here all day and try something for x in... We could go back up here where it was negative 1x plus 6 equals negative 13 plus negative 1x. We could keep trying and trying and trying, and nothing would work. So this is one where we say there is no solution. So when it gets to this part right here, you would say false. That's not true. 6 does not equal negative 13. That's false. So once we get to that point and we say, you know what, the x's disappeared, I ended up with this crazy statement that's not true, I'm going to say this has no solution then. Okay, I will tell you this. All of the problems that you're practicing in the 10 to 14 evens and the 28 to 32 evens, just try not to confuse matters today. All those problems that you practice, those 6 problems, will either turn out one way or the other here, okay? You'll either have an identity, and you'll say the solution is all real numbers, but you actually have to write that as your solution, okay? You don't just stop, you say and say it's an identity, you also say, okay, this tells me that the solution is all real numbers. Or maybe this happens. Then you say, oh, I ended up with no variables left. I ended up with this statement that's not true. It's false. I have to state that there is no solution. Okay? So that's what should happen in 10 through 14 evens and the 28 through 32 evens. One of those 2 situations should happen. And it's going to just depend on what happens when you're solving. Anybody have any questions on that before we practice what like number 33 would be in our homework? Okay, then let's go to the back side, our application problem. Then we get Marlo. Okay, who wants to volunteer to read out loud about Marlo here, our paragraph? Read out loud, the rest of us will follow along. Volunteer? Thank you, Joseph. Okay.
Probably not.
No, go ahead.
No.
You had your head down, so that's why I picked on you.
Well, I'm not gonna read it.
Maisie?
Marlo wants to rent a bike. Green Lake Park has an entrance fee of $8 and charges $2 per hour for bike rentals. Oak Park has an entrance fee of $2 and charges $5 per hour to bike rentals. He wants to know when the cost will be equal.
Okay, so he has a couple of choices here, doesn't he? He can either go bike at Green Lake Park and what it's going to cost in there, or he can go to Oak Park. He wants to know when would the cost be equal. In other words, when does it not matter? If this is how many hours I wanted to bike, it would not matter which park I chose. Okay, so we're going to write an equation for this, and we're going to. What we need is we need those 2 costs to be the same. So we're going to say when Green Lake Park, when its cost is the same as the other park, which is called Oak Park. And the reason we're just doing this in words first is so that it just kind of helps us be able to say, well then, here's what I would do to find Green Lake Park's cost. Here's what I would do to find Oak Park's cost. And then I would have my equation to solve. So after that, and this is kind of the process I want you to follow in that problem you're gonna do in your homework also, okay? So is there an unknown in this? There are some things we know, but is there anything that we don't know? What's something that we know? For Green Lake Park, what do we know? What's one of the things we know in that one? Talia, can you tell me? One of the things that we know for Green Lake Park? Entrance fee of $8. How many times do you think you gotta pay that? Every hour, every one time to get in, right? Entrance fee means one time to get in. Okay, what else do we know about Green Lake Park? Give me something else that we know about them. Preston, can you figure out something else we know about Green Lake Park?
They charge $2 for bike renter every hour.
Yeah, $2 every hour, okay, to rent one of their bikes. Okay, do we know anything else about Green Lake Park? Okay, that's it. What's the unknown in that then? What's the unknown for Green Lake Park? Well, we don't know what the cost would equal, but how would we be able to figure out the cost would be another unknown? Let's see, how many hours? We don't know how many hours, so it is dependent upon how many hours you rent the bike for, right? Okay, so the number of hours is unknown in that. How about Oak Lake Park? Or Oak Park, I mean, there's no lake in that one. Oak Park, what do we know about Oak Park? Samuel, what's one thing we know about Oak Park?
Has an entrance fee of $2.
Okay, they charge $2. How many times? One time, okay? What's another thing that we know, Blake, about Oak Park?
They charge $5 per hour for bike rentals.
Okay, so they charge $5 for every hour that you rent a bike. What's the unknown in that one? Adam?
The number of hours.
We don't know the number of hours. Yeah, it depends upon the number of hours rented.
So let X be the number of hours.
Yeah, so let's let X be the number of hours for both of them, because both of them have the same unknown. So X can be the number of hours, and not how much per hour. We already know that. What we don't know is how many hours, right? Okay, so then in step 2, so in step 1 we always describe our variable. Step 2 we actually write our equation now. So how could we represent Green Lake Park's cost in an algebraic expression? They charge $8 how many times? Once. Plus what else are you going to have to pay? $2 per hour. How could we represent that? To H, well we picked X, so we'll use X, right? You can use H if you want, though. Change the X to H. Okay, is there anything else Green Lake Park it's going to cost? $8 plus $2 every hour. Anything else? No? Okay. Equals Oak Park. Okay, go ahead and on your papers right now, you finish this equation. What do you think the algebraic expression on the other side of the equation would look like? Okay, who wants to share with us the algebraic expression that they have for the other side? Adam?
2 plus 5.
You guys agree with them? 2 plus 5.
2x plus 5.
2x plus 5.
Actually, no, it would be 5x. Yeah, 5x.
So the 2 is not going to have an x and the 5 is. Is that what I'm hearing? Okay. Do we agree? So $2 one time. This is their entrance fee, and $5 for every hour. Okay. So now all we need to do is we need to solve it. That's what we're going to do in our next step. Any simplifying to do in this problem? Do we have any simplifying to do on the left side? No. How about on the right side? No. So are we ready to solve it?
Yeah.
That's what we're doing in step 3. We're solving. Okay? So what are we going to do first here?
Subtract the 2h, or 2x.
Okay. Subtract 2x. Okay. What's the left side have left?
8.
Okay. How about the right side? What's that? 2 plus 3x. Okay. Now what? There's not a,
Now you
there
subtract
aren't
the
two things
two.
over here, there's two things over here, so which one should we get rid of?
Subtract the two.
Yeah, let's subtract the 2, let's do that, not subtract the 8. That gets us in trouble, lots of us. So the side that has 2 things on it, let's work with that side. So we have 8 take away 2,
6. And then divide that by 3. And then x equals 2.
okay? So, the first question asked was this. He wants to know when the costs will be equal. So what sentence could we write here? The cost will be the same when?
Every 2 hours.
For 2 hours, not every 2 hours, but for 2 hours, right? I don't think it would be every 2 hours, because then 4 hours we could check to see if it would be the same. The cost will be the same.
So are we writing that on 6?
Nope, right here. For 2 hours. That's B, by the way. That's just part B. So we're answering part A, where it asks when, after how many hours would the cost, you want to know when the cost would be the same. Well, that's after the number of hours. So the cost will be the same for 2 hours. Now I just want to explore something. Well, let's do part B and then we'll explore what Adam said here. So what would that cost be? Remember, it's the same. What do you think? Do you think we have to put it into back into our equation, put 2 in for x into the whole equation, or could we just use one part or the other? Does it matter which part we use? Why not? Because they're going to be the same, right? So we have 2 choices here. We could choose to either do it for Green Lake Park, which then we would use the 8 plus, how much do they charge every hour? 5? No. 2. They're the $2 an hour one, aren't they? Okay. So we could put it into that one, or we could put it into the other parks, and that one is the 2 for the entrance fee, and they charge. So they have a smaller entrance fee, but they charge less per hour, or more per hour, I mean. Okay, so it doesn't matter which one you plug it into, it should turn out to be the same, shouldn't it? So we're going to put in what for x?
2.
2. So 8 plus 2 times 2. What do we do first? Do we add 8 to 2? Or do we multiply the 2's?
You.
Multiply the 2's, yeah. And what does that become? 4, and 8 plus 4 is 12. Okay. Now, we really only need to do one or the other. That's why we put the word or in there. But should we get the same thing in the other one, if we did it right? 2 plus 5 times 2. Remember that after 2 hours, they're the same. So we have 2 plus what? 10. And 2 plus 10 is 12. So we get 12 either way, don't we? So what sentence are we going to write now?
Table, 2 at 2 hours equals 12
Okay.
dollars.
Okay, so could we say it maybe like at 2 hours, I guess you could use the number 2. At 2 hours, the cost is $12 for either one, right? And that one cost. What is that cost? So it's kind of like we're kind of combining it took 2 hours, at 2 hours. So you know what Marla was thinking, I only have a couple of hours to do this. Which part should he go to? Both of them would be one, so he only has 2 hours. Think you can do both of them? Okay, then does it matter which one he does? No, then it doesn't matter, does it? Okay, now I just want to explore something that really quickly that Adam said, because I want us just to see what would happen if we said every 2 hours, because that would, are we stating it correctly? Every 2 hours, so every 2 hours the cost would be the same. What would be the next same cost then? Every 2 hours. 2 hours, what would be the next one? 4 hours. So it's kind of like saying 2, 4, 6, 8, no matter what, as long as you pick one of those. So let's try the 4, okay? What's 2 times 4? 8. What's 8 plus 8? 16. So at Green Lake Park, at 4 hours, it would cost $16. How about over here at Oak Park? What's 5 times 4? 20. What's 20 plus 2? 22. So $16 for 4 hours at Green Lake Park, $22 for 4 hours at Oak Park. Are they the same? No. How many times do you think they will be the same? How many times will they be the same? Okay, what did we just learn? When will they be the same? What did we learn? When we were solving this, did we say the cost would be the same at 2 hours? So there's one time for sure, right? Are there any other times, do you think? Okay, give me one you think it might be. We need to explore this and find out. Maybe there is. Is there another one? What do you think, Kristen? For 1 hour? Is that what you're holding a finger for? No?
I thought you just said to hold it.
So, is there only one time frame, 2 hours, that the cost will be the same? Yes. If there were others, we would have gotten an all real number solution, wouldn't we have? Yeah. If there hadn't been any time, then we would have gotten a no solution one. But no, we found out that there is a time, and it is when that cost, it's when he rents the bike for 2 hours, exactly 2 hours. Okay, let's go to work on your homework.